Okay, good afternoon, gang. Things today might look and sound a little different than they normally do. My work computer died last night, so I'm using a plug-in mic and a plug-in webcam on my 13-year-old laptop. But I've been working with it through the day and got most of the kinks ironed out. Things seem to be more or less as they ought to be now. So we're going to go ahead and get started. This, of course, is MAC1140, Section 4. And today is the 7th of October. Today, we've covered pretty much all the stuff we need to cover on polynomials. But I wouldn't mind looking at one more example. And if there's a polynomial problem from the homework that you want to look at, feel free to type that problem number into the chat. I'll try to make those examples the ones you want. But the other thing we got to do is talk about rational functions. And rational functions are functions that are ratios of polynomials. In other words, fractions where the top and bottom are both polynomial functions. So, yeah, without further ado, let's dive in. I mean, this is really the whole plan for today. So, what problems would you like to see, Lily? Oh, no, don't do this. Ah, shit. No, my mouse is messing up. God damn it. No. I might be in real trouble here, guys. I'm sorry. There we go. All right, good. Okay. So yeah, Lily, go ahead and let us know which problems from the polynomial homework you would like to work on, and we will do that. We'll get right to it. No, it is fucking up. Oh, shit. All right, we'll get through this. This will work. All right. Let's do it then. So, a fun question related to this problem, and I'll use the numbers you have, but before that, you've seen in college algebra, or maybe algebra 2 in high school, that some quadratics, I'm going to put it in quotes here, don't factor. And by that I mean they don't factor over the real numbers. These are the quadratics that, when you set them equal to 0, don't have any solutions, or the solutions are not real numbers. So I have a couple questions. Are there, really quick, sorry, let me add one more thing to this. These are called irreducible. Yeah, YOU''VE. So you've seen that some quadratics cannot be factored nicely, cannot be factored over the real numbers. These are called irreducible quadratics. And my first question is, are there irreducible polynomials of higher degree? And can we factor irreducible quadratics using non-real numbers? I actually answered the second question in passing on Monday, but I'd like to give it a really clear answer. So first, is it possible to have an irreducible cubic? The short answer is no. All polynomials can be factored into products of linear factors and irreducible quadratic factors. So there's no such thing as an irreducible cubic. And in fact, if you think about the end behavior for a cubic, one side points up, the other side points down. That means somewhere in between, you had to have an x-intercept. And that x-intercept corresponds to a factor. So polynomials of degree 3, 4, 5, 6, 7, 8, 9, they can always be factored down into linear factors involving real numbers and irreducible quadratic factors involving real numbers. The second question the answer to the second question is yes. Even irreducible quadratics can be factored using their complex roots. So complex numbers are very cool things. I could spend days, weeks, years even talking about complex numbers, and if you're interested in that sort of stuff, I want to encourage you to take, what was it, MAA, I think 4301, which is the Intro to Complex Variables class. But the short answer there is yes, yeah, any polynomial can be broken all the way down into linear factors if you're willing to work with complex numbers. For example, the quadratic x squared plus 1. This is irreducible. Over the real numbers. If you use the quadratic formula, you'll find that it has complex roots. Well, let's do it. X equals negative b, that's 0, so negative 0, plus or minus b squared, that's 0, minus 4 times a times c. That's 4 times, minus, so 0 minus 4 times 1, all over 2a, which is 2. So that's 0 plus or minus the square root of -4 over 2, which is plus or minus 2i over 2. Right? So you have to remember how square roots of negative numbers work. The square root of -1 is I. So if you have the square root of some negative number, you'll just have I times the square root of the positive version of that number. The square root of 4 is 2. So this numerator here, the square root of -4, is 2 times I, because the square root of the negative is I, the square root of the 4 is 2. And you can cancel the 2's, and you get plus and minus I. This means that x squared minus 1, my polynomial p of x here, can be written as x minus I times x minus negative I, or just x minus I times x plus I. So when you break a big polynomial down into linear factors and irreducible quadratic factors, you can further work on that irreducible quadratic using the quadratic formula to get his complex roots, and then factor him the same way we did yesterday when we used the quadratic formula, sorry, I should say Monday, when we used the quadratic formula to factor that difficult quadratic at the end. So this connects to something called the fundamental theorem of algebra, which we didn't get time to discuss on Monday. So I'm going to go ahead and give you that, and then we'll solve the problem that Lily gave us. Or did we get to? I don't know. I think we stopped short, right? Sure. So we found the roots of x squared plus 1 using the quadratic formula because, try as we might, we couldn't figure out how to factor it. Quadratic formula told me that those roots are positive I and negative I. And any polynomial can always be factored using its roots as x minus whatever root times x minus whatever root. Once you have the full list of roots, you have the full list of factors. You can check that if you multiply this back out, you do get x squared plus 1. You'd have x squared plus ix minus ix minus I squared. And that's x squared plus x squared minus -1. Okay. So, fundamental theorem of algebra says every polynomial of degree n has exactly n roots counted with multiplicity and can be factored as p of x equals x minus r1 times x minus r2 times x minus r3 times all the way out to x minus Rn, where the numbers R1, R2, R3, all the way out to Rn are the possibly complex, i.e. not real, roots of P. So there might be some repetitions here. You might have x minus 1 times x minus 1 for your first two guys, and then your third guy might be x minus I. But if you know all the roots, then you can write down the factored form of the polynomial. There might be a coefficient out front here, but the main thing is once you know the roots, you know the factors. And if you know all the roots, then you automatically know all the factors. A neat fact, and you want to remember this, non-real complex roots always come in conjugate pairs. This meaning if A plus BI is a root, then so is A minus BI. So this is called the complex conjugate of this number. So if you know that you have a root that's like 1 plus 2i, then automatically you know that there's another root 1 minus 2i for that polynomial. All right. So I'll give you a second to write here while I copy down the problem that Lily wanted us to look at. We've got x to the 4. Plus 5x squared minus 36 into linear and irreducible quadratic factors and just linear factors. So what the fundamental theorem of algebra up there tells us is that if you know all of the complex roots of your polynomial, you can always factor it all the way down into linear factors. That's neat. That's the second part of this problem that we're going to look at. But the first part of this problem is to just see if we can break it down into real factors. And those real factors could be linear, and they could be irreducible quadratic, could be 2 linear and 1 irreducible quadratic, could be 2 irreducible quadratics, anything like that. The trick to factoring this particular polynomial p is a substitution kind of thing, where you think of this as x squared squared plus 5x squared minus 36. So in other words, it's kind of like u squared plus 5u minus 36. And we want to see if I can factor that. So we make the substitution. u equals x squared, just to make our lives look a little bit easier. Then p of x will look like u squared plus 5u minus 36. And I want to see if I can factor that guy. So I need two numbers that multiply to negative 36 and add up to positive 5. Let's see, 6 and 6 multiply to negative 36, but that doesn't add up to 5. How else can I split 36 into two factors? 12 and 3, but that doesn't add up to 5. 9 and 4, if we take those with the correct signs, those will do the job. So this piece right here, u squared plus 5u minus 36, I could rewrite that as u minus 4 times u plus 9. And then we just go back to the x's. What was u? Well, u was x squared, so this is x squared minus 4 times x squared plus 9. This piece is irreducible over the reals, but this piece factors further. X squared plus a constant is always irreducible over the reals, because it's a vertically up-shifted version of x squared. You know it won't have any x-intercepts. But the x squared minus 4 I can factor further as x minus 2 times x plus 2. So I get x minus 2, x plus 2, x squared plus 9. And that would be your answer for part A. Here I have broken p of x down as far as I can just using real numbers. To go any further, I would have to use complex numbers. Why is this ringing?
Why can't you do the same thing to x squared plus 9?
Because x squared plus 9 is irreducible. So difference of squares, we have a formula for the difference of squares. But a sum of squares, no such formula exists. So let me come to the side here and answer that question. X squared minus a squared always has two roots. It's x minus a times x plus a. And this is called the difference of squares. And if you think about the graph, this makes sense, because you take the x squared polynomial and you shift it down by a units, you get something that looks like this. So of course, yeah, he's got some roots, and those roots turn out to always be a and negative a. But if you moved him the other way, think about that graph. This guy doesn't have any x-intercepts. He doesn't have any real roots. So he doesn't factor over the real numbers. Because if he did factor, you know every factor gives you a root. But from the graph, we can tell that there are no roots because there are no x-intercepts. So there is no trick for factoring a sum of squares, at least not over the real numbers. I'm sorry to hear that, Gabrielle. Yeah, I am using some pre-compromised tech today. I will be very careful to write everything and ask you not to have to depend on listening too much. So try to pay extra careful attention to what we're writing. The question I'm trying to answer here is, why can't I do the same thing with x squared plus 9 that I did with x squared minus 4? And the answer is that if you shift a quadratic down, he will have some roots. But if you shift your quadratic up, he won't. So x squared minus a squared, he always factors like this. But x squared plus a squared will never factor because he doesn't have any roots. Yeah, this says sum of squares, question mark. Exactly, because of the plus. The plus tells us we're moving up rather than down. And if you take the x squared parabola and move him up, then he won't have any x-intercepts. So because he doesn't have any real roots, he isn't going to factor. All right. So this piece would be your answer for part A. For part B, we'd want to continue factoring this using the quadratic formula. So I use my quadratic formula, x equals negative b, b is 0, plus or minus the square root of 0 squared minus 4 times a, which is 1, times c, which is 9, all over 2a, which is 2. So that's plus or minus the square root of negative 36 over 2. The square root of 36 is 6, so the square root of negative 36 is 6i. So these roots are plus or minus 3i. Therefore, x squared plus 9, following my fundamental theorem of algebra, can be written as x minus 3i times x minus negative 3i. And this tells me that overall, p of x can be written as x minus 2 times x plus 2 times x minus 3i times x minus the negative here is x plus 3i. And that's the fully factored form of the polynomial x to the 4 plus 5x squared minus 36. So we're able to break him all the way down. What are we looking for, Ron? We want to see the rest of the problem or the theorem to the left?
Yeah, I just couldn't see the plus xi over 2.
Oh, okay.
Thank you.
Sure. All right. So remember last time we learned our rational roots theorem? And we have tricks like this one, this substitution trick here for factoring that we should have seen before, but if we haven't, it's not too bad. If all the powers of x are even, you can always make this substitution to try and make life a little bit easier. But the end result is using the tricks we already knew we can get to here, and then using the quadratic formula and the fundamental theorem of algebra, we can finish factoring this over the complex numbers. Let's try one more. Let me see what we can get. That looks fun. Irreducible quadratics, linear and irreducible quadratics. Let's take a look at number 28 also. You could try factoring this by grouping. That's an option. But I'd like to get us a little bit more practice using our rational roots theorem. So that's what I'm going to do. It's true that this can be factored by grouping. If I think of this first piece and the second piece as things on their own, I can pull an x squared here. Let's show that. That certainly is the fastest way to do it. So from this first piece, I can factor in x squared, and what's left will be x minus 3. And from the second piece, I can factor a 4, and what's left will be x minus 3. And this is nice because now I have a common factor of x minus 3. So I can write this as x squared plus 4, I'll space it out so you can kind of see what I'm doing, times x minus 3. So I'm pulling this common factor out on the right. So we'll get right away here to x squared plus 4 times x minus 3. And then the same trick for factoring x squared plus 4 works like we used for x squared plus 9. It will be x minus 2i times x plus 2i. Or, if you're not comfortable with this, you can use the rational roots theorem. My possible p's are divisors of 12. So that's 12, 6, 4, 3, 2, and 1. My possible q's are divisors of 1, that's just 1. So our possible rational roots is our plus and minus p over q. Remember where p is a divisor of the constant term and q is a divisor of the lead coefficient, are just plus and minus 12 over 1, plus minus 6 over 1, plus minus 4 over 1, plus minus 3 over 1, plus minus 2 over 1, and plus minus 1 over 1. So if you didn't notice that this could be factored by grouping, and not every cubic can be, right? Many of them can't be. This would be the thing to do. And you would start checking things off this list one at a time using synthetic division. I'm going to jump to checking 3 because I know that 3 works. I'll just show you how it looks. I would write 3 and then the coefficients here. So 1, negative 3, 4, negative 12. We bring down the 1. 3 times 1 is 3. Then we add these. 3 plus 3 is 0. 3 plus negative 3 is 0. Multiply these. 3 times 0 is 0. Add these. 4 plus 0 is 4. And then I multiply these. 3 times 4 is 12. Negative 12 plus 12 is 0. So my remainder is 0, which means that that 3 is a root, i.e. x minus 3 is a factor. And this is the quotient. So I would learn that from this procedure that p of x is equal to x minus 3 times 1x squared plus 0x plus 4. Or, like we got before, x minus 3 times x squared plus 4. So we get there either way. The rational roots theorem is the more powerful tool, but factoring by grouping is a nice thing that works sometimes. What's necessary in order for factoring by grouping to work is that when you pull out as much as you can from the first two and as much as you can from the second two, you have the same thing here and here. As long as you have that, factoring by grouping will work. But there are many problems where it doesn't, but the rational roots theorem does work. So keep in mind, you can always use the rational roots theorem. For factoring into linear and irreducible factors, we're done. This is a linear factor, and this is an irreducible quadratic factor. So that's it. But if you wanted to factor entirely into all linear factors using complex numbers, this would be x minus 3 times x minus 2i times x plus 2i. So a minute ago you asked, is there a formula for the sum of squares? Yes, but not involving real numbers. The formula for the sum of the squares is the thing that you think you're seeing in these last few problems. X squared plus 4 factors as x minus 2i times x plus 2i. X squared plus 9 factored as x minus 3i times x plus 2i. X squared plus a squared in general factors as x minus ai times x plus ai. It's not a formula that's often taught in algebra classes because it involves complex numbers, and usually we like to keep our focus on real numbers. But for this portion of this class, we do fiddle a little bit with complex numbers. Complex analysis is a beautiful field. I can show you some things that are really gorgeous, just purely geometrically, using complex numbers. But it's not something we have time for, I'm afraid. It's not a part of this class officially. But this stuff is. All right, so make sure you're comfy factoring these polynomials first down to linear and irreducible quadratics. Sometimes you'll need the rational roots theorem for that. That's good. And then make sure you're comfortable taking arbitrary quadratic functions, any quadratic function, and factoring it over its complex roots. Okay. I'd like to do one more problem involving polynomials, and then I want to talk about rational functions. I would like to find a polynomial with real integer coefficients having roots (1, -3, and 2i). Remember that every root corresponds to a factor, and every factor comes from a root. So the root at 1 tells me that x minus 1 is a factor. The root at -3 tells me that x plus 3 is a factor. And the root 2i tells me that x minus 2i is a factor. But if I just multiplied these three factors, I would not get a polynomial with real integer coefficients. So far, my polynomial looks like x minus 1 times x plus 3 times x minus 2i. What other number must be a root of this polynomial? Think back to that fact that I mentioned a minute ago. Good. -2i must also be a root, since 2i is a root, so must be -2i. Therefore, x plus 2i is a factor. So my polynomial is this guy. Now we could multiply all this out and verify. This is x squared plus 2x minus 3 times x squared plus 4. And then we can distribute, and I'll get x to the 4 plus 2x cubed minus 3x squared. That's distributing the x squared across this trinomial, plus 4x squared plus 8x minus 12. And so altogether we get x to the 4 plus 2x cubed plus x squared plus 8x minus 12. And we could have gone the other way. I could have given you this guy and asked you for the factored form, or a list of roots. And here you would need to begin using the rational roots theorem. The rational roots theorem would pick up the root at 1 or the root at -3. Which one you would find first kind of depends on what order you check them in. Once you've found those guys, you would have this. And then to finish things up, you would factor each of those pieces. All right. So you guys now know as much about polynomials as any other calculus student. The trick from here is to make sure you remember this stuff and to start trying to make connections. So as you go through the homework, every problem that asks you to draw a graph, do yourself a favor, draw it by hand. By first using the end behavior and then using the local behavior near the roots. I will ask you to do that on exams. Your brain can take it, I promise, although I understand if it's very intimidating. Uh, when I was a college student, this is the stuff that we were doing in the first week of my MAC1147 class, and I remember coming home going, oh my god, I'm so fucked. And I just sat there for like 8 hours that night, grinding on problems from the book and reading examples and working them. And eventually it came out okay, and that class ended up being a real game changer for me. So as intense as it may feel, as you can do it. I know you can. Um, it's just a matter of putting in time and staying focused while you work. So work these problems. Draw the graphs by hand. Look at the factors and see how they affect the graph. Look at the graph and see how it could tell you factors. Remember to use end behavior. And remember to work in a distraction-free environment. Don't let yourself get pulled away by other things. Turn off your phone. Um, there's a lot that you can do to help yourself. Try doing it in 30-minute chunks. Say, okay, I'm going to turn off my phone, but just for the next 30 minutes. Anything can wait for 30 minutes. And just focus on that for 30 minutes. And then take a break, whatever, turn on your phone, go for a walk, grab a coffee. But then come back and do that again. As long as you really are diligent with putting the effort in and giving it your exclusive, undivided attention while you're working, not only will you learn this, but you will remember it. You can do it. I know everybody here can. So, the next topic is rational functions. And I have to remind myself what section this is in the book. Oh shit, and I'm on my home computer, so I don't have that. All right. The definition of a rational function isn't as intimidating. Function f of x is called rational if it can be written as p of x over q of x, where p of x and q of x are polynomials. So it kind of leans on the definition of polynomial. Examples like this is a rational function. F of x equals 1 over x is a rational function. It's kind of silly, but any polynomial on its own is a rational function. Because I can think of this guy as himself divided by 1. And the quadratic upstairs, along with the constant downstairs, both of those are technically polynomials. Something that's not a rational function like f of x equals x squared plus the square root of x over x, this is not a rational function. Because the top here, x squared plus the square root of x, isn't a polynomial. Because the power of x here is 1/2, which is not a whole number, right? So if polynomials are like the function version of whole numbers, then rational functions are like the function version of rational numbers, i.e. fractions. Graphing rational functions is a little bit trickier than graphing polynomials. We've seen that once you know the factors of a polynomial and the end behavior of a polynomial, you can sketch its graph really nicely, and we've done lots of that. You may want to remind yourself, right? We did that on Monday, where we looked at the end behavior. Actually, we did that last Wednesday. We looked at the end behavior and the local behavior near the roots, and we used that to sketch the graph of any polynomial. Rational functions kind of obey the same rules as polynomials, except the denominator makes things a little bit more complicated. So there's two sort of new concepts that we need to talk about for a rational function, and those are asymptotes, vertical asymptotes and horizontal asymptotes. Any questions on why any of these are or are not rational? If not, then I want to introduce these new ideas here. I guess the first thing I should talk about here is the domain of a rational function. Remember, the domain of a polynomial is always all real numbers. The domain of a rational function, f of x equals p of x over q of x, is all real numbers except those which make the bottom equal to 0. This is a good thing to know, because if you want to sketch the graph of a function, you want to know its domain. The two kind of new concepts that we're going to meet here have to do with the end behavior. So remember, when we started talking about polynomials, we talked about their domains, how they're always smooth and continuous, and then we talked about their end behavior. For a rational function, the end behavior question is a lot more exciting. This is where we introduce the concept of a horizontal asymptote. I'll show you a picture an example of a rational function. I'm not going to tell you the formula for this guy just yet, because it doesn't matter for what we're doing right now, but soon we will look at that. If this dotted line here is the line y equals 1, and this is the graph y equals f of x, then I would describe the end behavior as follows. As x goes to negative infinity, remember this notation, the arrow or goes to notation we used when we talked about end behavior of polynomials. We use it for rational functions too. If I let x wander really, really, really far off to the left here, then my y values are getting closer and closer and closer to this horizontal line, which is y equals 1. So as x goes to negative infinity here, I would say y goes to 1. And as x goes to positive infinity here, I would also say y goes to 1, because again, as we wander really, really far out this way, the y values are getting closer and closer and closer to that line. This is what we mean by horizontal asymptote. And here we would say that the line y equals 1 is the horizontal asymptote for f of x, because the graph gets closer and closer and closer to that line as you go further and further and further away from x equals 0. There's actually lots of kinds of asymptotes. You can have a horizontal asymptote like this. You could have a slanted asymptote, like y equals x could be an asymptote. Those are called oblique asymptotes. But for us, we're going to focus just on horizontal and vertical asymptotes. That is enough for us to worry about right now. In general, here's the definition. If, as x goes to plus infinity, y goes to some number L, or as x goes to negative infinity, y goes to L, then we say the line y equals L is a horizontal asymptote, and I'm going to, I'll write it this one more time, but from here on I'll abbreviate horizontal asymptote as HA for the function y equals f of x. Right. And this is a place where Desmos can be useful to fiddle around. You can also generate tables in your calculators. That can be fun. But let me show you one or two more neat examples. I'll give you just a second to write, and then I'm going to flip over to Desmos. Okay, going to Desmos. This is a rational function, 1 over x squared plus 1. The polynomial upstairs is 1, it's the constant function, and the polynomial downstairs is degree 2, it's x squared plus 1. And if I toss in the line y equals 0, I'll make it dotted, why not? You'll notice that as I wander further and further and further off to the right, the graph of my function sits down closer and closer and closer to that line. And also, as I wander further and further off to the left, the graph of my function, the red, sits down closer and closer and closer to that blue dotted line. This is that goes to notation in action. As x goes to negative infinity, so as my x's get more and more negative, my y values get closer and closer to 0. So here I would say that y equals 0 is a horizontal asymptote for this function. If I fiddle with the numerator a little bit, this guy still has y equals 0 as a horizontal asymptote. But if I make the top x squared instead of just x, things change. So looking at this graph, can anybody tell me what they think the horizontal asymptote for this function is? Yeah, this one is y equals 1. And again, you'll see, as we wander further and further off to the right, my graph gets closer and closer and closer to that y equals 1 asymptote. So this is saying that as x goes to positive infinity, y is going to 1. And on the left-hand side, as x goes to negative infinity, those y values are also getting closer and closer and closer to 1. Look, like 0.997. And if you go further to the right, the y values will be closer to 1. There's a rule for finding these. Given a rational function, f of x equals p of x over q of x, you have to break it into 3 cases. If the degree of the top, p of x, is bigger than the degree of the bottom, q of x, it's like if the top has an x cubed in it and the bottom just has x's and x squareds, then there is no horizontal asymptote. If the degree of the top is less than the degree of the bottom, we saw 2 examples like that just a second ago, and they both had y equals 0 as the HA, and that's true in general. So if the degree of the top is smaller than the degree of the bottom, then y equals 0 is the horizontal asymptote. The fun case is if the degrees match. Then the horizontal asymptote will be the line y equals the ratio of lead coefficients. And I'll show you an example here, but first just write it down. Okay, I think the first two cases are pretty self-explanatory. But that third case, I want to look at an example there. And I kind of want to show you why it's true. So here I have a rational function. The numerator, the top, p of x, is 6x to the 4 plus 3x cubed minus 2x squared plus 1. And the denominator is 2x to the 4 minus 5x squared plus 7. So the degree of the top, p of x, is 4. And the degree of the bottom, q of x, the largest power of x, is also 4. So we're in the third case, where the degrees match. That means that the horizontal asymptote is y equals the ratio of lead coefficients. So what the fuck does that mean? Well, that means you take the lead coefficients and you form a ratio or fraction out of them. The lead coefficient of the top is 6. The lead coefficient of the bottom is 2. So I form the ratio 6 over 2, which is 3. So, i.e., y equals 3 is the horizontal asymptote. The reason this works is because if you were to divide every term in this whole fucking thing by x to the 4, you would get 6 plus 3 over x minus 2 over x cubed plus 1 over x to the 4 upstairs. I'll write it. This is equal to 6 plus 3 over x minus 2 over x cubed plus 1 over x to the 4, all divided by 2 minus 5 over x squared plus 7 over x to the 4. So if I divide top and bottom by x to the 4, that's what I get. Now imagine plugging in a very, very big number for x. The 6 would stay a 6. the 3 over x would be small because the x is huge. And if you take a fraction where the top is small and the bottom is huge, that whole thing is small. If x is huge, then x cubed is even huger. So 2 over x cubed would be even smaller still. 1 over x to the 4 would be unimaginably tiny. And the same is true for the 5 over x squared and the 7 over x to the 4. So if you put in a really, really, really big number for x, these things are almost all 0, and you just get 6 over 2, which is 3. In other words, as x goes to infinity, as you put in bigger and bigger numbers for x, all of these lower order terms matter less and less, and it's these two lead terms that really tell you what's going on. That's why the rule works. And when you take Calc 1, I will prove this rule to you. Hopefully, if you take it with somebody else, they'll prove it to you as well, using the notation and rules behind limits. But we're in pre-calc, we don't have limits. This is good enough for us. Those are horizontal asymptotes. They're not too bad. The next thing we need to talk about are vertical asymptotes. If, as x goes to some number c, y goes to infinity, or as x goes to some number c, y goes to negative infinity, then we say that the vertical line x equals c is a vertical asymptote for the rational function f of x. Indeed, this is true in general, regardless of whether f is rational or not. And for rational functions, vertical asymptotes which I'm going to call VAs, come from roots of the denominator. Now you do need to watch out. If there's a factor that cancels top to bottom so that there is no factor left downstairs, then that won't produce a root, that will produce a whole. So these come from roots of the denominator after you have factored the top and bottom and canceled anything that can be canceled. That's it. That's how you find vertical asymptotes. So you factor the top and the bottom, cancel anything you can cancel. Any factors that are left over on the bottom will give you a vertical asymptote. So for example, if I had x squared plus 6x plus 9 over x plus 3 times x minus 1 times x plus 2, I can factor the top. The bottom's already factored. If it wasn't factored out, I need to factor it, and that's why we learned this shit right after learning how to factor big polynomials. Can factor the top. the top is x plus 3 squared. It's x plus 3 times x plus 3. So I get x plus 3 times x plus 3 over x plus 3 times x minus 1 times x plus 2. I can cancel these guys, and what's left is x plus 3 upstairs and x minus 1 times x plus 2 downstairs. So if this is f of x, then this will have vertical asymptotes x equals 1 and x equals negative 2. That's it. So to find vertical asymptotes, you factor top and bottom, cancel any shit that can be canceled, and then look at the remaining factors downstairs. Whatever makes those factors 0 will make your function undefined, of course, but what's more, you'll also have a vertical asymptote there. So in other words, you find vertical asymptotes through a very similar process used to find the domain. All right? You set the bottom to 0. Just make sure you factor and cancel when you're looking for VAs. The last thing I'd like to do with you today is sketch a graph of this function using everything we know. So let's sketch the graph of f of x equals this thing, x squared plus 6x plus 9 over x plus 3, x minus 1, x plus 2. First, I want to write down the domain. The domain is all real numbers except for those which make the bottom 0. And I have to use the original guy for this. Just because this factor cancels doesn't mean he doesn't affect the domain. So that's all real numbers except x equals negative 3, negative 2, and positive 1. Or in interval notation, negative infinity to negative 3, unioned with negative 3 to negative 2, unioned with negative 2 to 1, unioned with 1 to infinity. My vertical asymptotes. We just did that. When you factor the top, the x plus 3 cancels, and you get another x plus 3 over x minus 1 times x plus 2. So there's two vertical asymptotes. They are x equals 1 and x equals 2. Be careful on all of these asymptote questions. They need you to give the equation of the line. You can't just say 1 and 2. You have to say x equals 1 and x equals, I'm sorry, it should be negative 2, shouldn't it? Negative 2. When you give the horizontal asymptote, you can't just say 0, you have to say y equals 0. And that is the horizontal asymptote here, because the degree of the top is 1, the degree of the bottom is 2. Or you can look at the original also. Here the degree of the top is 2, and the degree of the bottom is 3, because it's x plus 3 times x minus 1 times x plus 2. So if you multiplied this all out, it would be an x cubed downstairs, x squared upstairs. Or if you use the canceled version, it's degree 1 over degree 2. And either way, the bottom is bigger than the top. The degree of the bottom is 1 larger than the degree of the top. So the line, I'll say the degree of the bottom is bigger than the degree of the top. So y equals 0 is the HA. Okay, moving from here, let me just copy this down. This is x plus 3 over x minus 1 times x plus 2. I'd also like to find my intercepts. So my x-intercept here is going to come from when the top is equal to 0. Now the top is equal to 0 here when x is equal to negative 3. Right? When is a fraction, like this whole big thing, equal to 0? Well, this whole big thing is equal to 0 when the numerator is 0. That's how fractions work. So this means when x is equal to, negative 3. My y-intercepts, it's only ever one of them, and it always comes from plugging in x equals 0. That's true for every function, not just rational functions or polynomials. So if I plug in x equals 0 here, I get 0 plus 3 over 0 minus 1. So that's 3 over negative 1 times positive 2. That's negative 3 halves, or negative 1.5. This is enough to get a pretty good graph. The only other thing I would want to comment is, since we canceled a factor of x plus 3, top to bottom, there's a hole at x equals negative 3. So our x-intercept is actually a hole. In other words, we don't actually touch the x-axis there. We're going to come up to it and then have a little hole. I'll show you what I mean. I begin by drawing in my asymptotes. The HA is the line y equals 0. Then I draw in my vertical asymptotes. So I've got one over here at negative 2. And I label that. Always label all this stuff. Don't just draw it, label it. My other VA was at x equals 1. I said there's kind of two interesting things going on at negative 3. I've got a hole which would otherwise have been an x-intercept. So I'll go ahead and draw in my hole there. And I know that my y-intercept is negative 3 halves, or negative 1.5. So here's negative 1, here's negative 2, here's my y-intercept. This isn't a whole lot to get started with. I know that I need to approach these horizontal asymptotes, and I know I need to blow up to infinity at these vertical asymptotes to get a little bit of a feel for what's going on in each of these regions. I'll plug in an x value. So maybe over here to the left of negative 3, I could plug in negative 5. I'll do the work up here. F of negative 5 is negative 5 plus 3, that's negative 2, over negative 5 minus 1, that's negative 6, and negative 5 plus 2, that's negative 3. So this is negative 2 over negative 18, or positive 1/9. In particular, I care that it's positive. So that tells me that I'm going to be approaching my horizontal asymptote over here from above. So then I know that I had to have done something. Let's see, negative is not correct. Negative 5 plus 3 is negative 2. Oh no, I'm sorry, this should be negative, right? Yeah, because the downstairs here are both negative. That's positive, so this is negative. All right. So here's my point, negative 5 comma negative 1/9. And that tells me, because I'm negative there, that I'm approaching my horizontal asymptote from below. So then I come here. This was going to be an x-intercept. So I would go like that. And then I approach my vertical asymptote like this. Down here, I know my function is negative, and I don't have any x-intercepts in here, which means that I have to approach these vertical asymptotes like this. No other choice. The only way I could approach like this or like this is if I had an x-intercept in here somewhere. And over here, I will return like this and then settle down on this horizontal asymptote, like this. And that's a really nice graph of this rational function. There's one last thing that I would like to say about rational functions, and it will be very helpful when it comes to drawing graphs. You know how with polynomials, if you have a root of odd multiplicity, you cross the x-axis, and if you have a root of even multiplicity, you bounce off the x-axis? Something similar is true about vertical asymptotes and rational functions. If your vertical asymptote is coming from a factor of odd multiplicity, and here these are both odd multiplicity, then you will change sign as you jump over that vertical asymptote. So this guy came from an odd multiplicity factor of the denominator x plus 2. And since I know I approach him going up on the left, that means I have to approach him going down on the right. Similarly, this guy came from an odd multiplicity factor of x minus 1. Since I approach him going down on the right, I know I have to come back going up, down on the left, I know I have to come back going up on the right. I'll talk more about that next week when we talk about solving rational inequalities. But I'll say this for your homework this week. If you are having a difficult time coming up with the graph that you need, first, vertical asymptotes, horizontal asymptotes, x-intercepts, y-intercepts. Then, if that's not enough to give you a good picture, start plugging in a few points. Once you know whether you're positive or negative, say over here, you can draw this arrow in, settling down on your horizontal asymptote from above. Or over here, since I knew I was negative over there, I could draw my arrow settling in on my horizontal asymptote from below. And I could have added a few more points in different places here if I wasn't certain where the graph was. But then you add in your behavior near the asymptotes, just those arrows, and connect them using nice smooth curves. Very similar to how we graphed polynomials using end behavior and local behavior near roots. So I'll talk a lot more about this, graphing rational functions and whatnot next week when we start talking about solving rational inequalities. But that is where I will leave you guys for today. I do have an office hour this afternoon. If you want to come by and chat about anything, I'll be moving over to that immediately. Otherwise, I will see everybody on Monday. I hope you guys have a lovely weekend, and reach out to me if you would like help with anything. Okay. So if a function has x in the denominator, then it isn't a rational function? No, having x in the denominator isn't a problem. Having x in the denominator is just fine for rational functions. The top and bottom both have to be polynomials. That's all to be a rational function. And then Seb had to go to work. Yeah, class videos will be up on YouTube. Just look at the announcement where I post the link for the Zoom meeting, right? So as soon as I finish uploading that, I'll post the link there. Yeah, if you have an extension request that you put in, I'll be blasting through those during my office hour, or if the office hour is very busy, I'll be doing it afterwards. But yep, if you need something extended, just go ahead and submit an extension, and I'll go in there and clear them out. I'm fine with you working on those whenever. Any other last minute questions? Alrighty then, I will see you guys either in office hours or Monday. Take care, have a good weekend.